Hey everybody, it's Jenny Civey from Norman Wright. In the last couple of videos we've covered the basics of HVAC from a high level and system pressure and load equations. So I think now we're ready to get into the components. Louvers, dampers, coils, and fans make up the components of an air handler, so that seems like a good place to start, and it's also the components of many other parts of the HVAC system. Since the air comes in through the louvers, let's start there. Let's talk about what's a louver. I wanted to start by showing you some pictures of building louvers. Let me spread these out so we can see them all. So if we start in the top left, you can see the louvers right here, and they're a nice architectural louver. Moving to the right, you can see the louvers here. These circles are the louvers in this bottom left, and then in the bottom right, the louvers actually are formed into a penthouse, which is often used to hide equipment on the roof. So you've probably seen tons of louvers and maybe didn't even realize they were louvers at the time. So let's go back to drawing our building from the HVAC overview video with our louvers on the top. Louvers can be used for intake or for exhaust. The general principles are the same, so I'm going to really just talk about the intake side. Louvers bring air into the building, but we want to keep other stuff out, like rain. So a louver is part of the HVAC system that allows the airflow into the building but blocks the rest of nature from getting in. Louvers may also contain filtration media, and they need to repel moisture, sand, and snow. They may also need to be resistant to high winds and even projectiles that may impact them during storms. Okay, let's make a little room. So let's draw a louver and talk about louver blades. A louver is made up of multiple blades, and these blades can have different shapes on what you need your louver to do or keep out. The blades are either extruded aluminum or formed steel. Louver blades can be stationary or adjustable. Stationary louver blades give the building a fixed look, while adjustable louvers provide control for airflow from full open to full closed. Stationary louvers are the most common type of louver you'll see, and they're suitable for almost any application. Adjustable louvers act like a damper and are often used in warehouses or other applications where you want to close the louver. Okay, let's slide this over and talk about blade types. Non-drainable blades may look like this. Rain that hits them will just fall down the face of the louver. Drainable blades are designed with a gutter that would direct rainwater to the ends of the blades for draining. Next we have sight-proof blades, which are shaped something like this. They're designed that you can't see through them, so they're often used to hide equipment. Next we have wind-driven rain blades. They're designed so that heavy rains driven by wind, such as in big storms, can't get into the building. You see these used in application where there's a dry room or equipment behind the louver that you don't want exposed to moisture. Their blades are a little more complicated, and they have little catches like this that help catch the water and keep it from getting in the building. Let's scoot this over and talk about acoustical blades. Acoustical blades have sound-absorbing material in them to reduce noise coming into or out of the building at the louvers. They're commonly seen in office buildings, condos, and public buildings. Combination louvers are a combination of fixed and adjustable blades. Fixed blades on the outside and adjustables on the back side. It's a louver and a damper in a common frame. So in the drawing, the blue is the fixed part and the green is the adjustable part, the damper in the back. And you can see if I rotated this into the vertical position, like this light blue color, it would close the damper off. Since louvers are on the outside of the building, there's an architectural component to them. You can get them in continuous blade lengths, so it looks like one long blade where the structure is hidden behind it. And you can also get them to match the building facade. There's a lot of architectural options when it comes to louvers. So let's move all this out of the way and talk about louver performance. Free area is the major factor of louver performance. You want to allow as much air as possible to pass through the louver while keeping the unwanted stuff, like water, out. Too much free area and the louver can't reject water. Too little free area and the airflow becomes too restricted. Higher free area means more space between the louver blades. Louvers will have a free area table where you can see by louver size their free area. So this is an example of a free area table, and let's say we wanted to pick a 48 by 48 of this louver. You can see that it would have 9.08 square feet of free area. You can find out the percentage of free area just by dividing 9.08 square feet by 16 square feet. It gives you 56.75% free area. Now we know that area times velocity equals CFM, so we can calculate the velocity of, let's say, 4,000 CFM through this louver. So 4,000 divided by 9.08 equals 441 feet per minute. The ASHRAE Fundamentals Handbook recommends 400 feet per minute intake velocity and 500 feet per minute exhaust, so we're in a pretty good place here. Okay, let's scoot this up and make some more room. So now that we know our velocity, we can look up the pressure drop across the louver at that velocity. We have 441 feet per minute, so that would be about here on this line. Draw it up to the intake mode line and across, and that gives us a pressure drop of about 0.03 inches. Now this table is for louvers without screens. With a screen, it's going to increase your pressure drop, maybe about 10%. Okay, I need a little more space. Water penetration resistance is one of the most important functions of wall louvers. The point at which measurable water passes through a louver is referred to as the beginning point of water penetration. Water penetration doesn't need to be considered in exhaust applications. Per the Air Movement and Control Association, AMCA, standard 500-L, the beginning point of water penetration is considered when 0.01 ounces of water penetration per square foot of louver free area occurs. You'll see it in the performance data as stated 0.01 ounces at 1,000 feet per minute, for example. A higher beginning point of water penetration will provide better protection. Water penetration is shown on a graph like this. From the title of this, you can see that for this louver, our beginning point of water penetration is 1,023 feet per minute, which is this point down here on the curve. So at 441 feet per minute, we are fine, but you can see how as your velocity increases, your water penetration also increases. The last thing to look at is wind loads and structural considerations. As louvers get larger, they'll be built in multiple sections and will require additional structure to handle the wind loads. You'll see wind loads shown as wind load of 30 pounds per square foot, equivalent of 110 mile-an-hour wind, for example. So that's an overview about louvers and louver performance. Don't forget to subscribe to this YouTube channel, and thanks for watching.